Continuing with our discussion about energy, we're going to look at machines, specifically some different simple machines that can be used to make our lives simpler. A machine is a device that makes a task easier. It can either do that by changing the direction of a force, or it can multiply the amount of the force. So both are ways that a machine is used, and a lot of times different machines are put together into more complex systems. But we're going to focus on single, simple machines in this video. An important idea is that the machine does not change the amount of energy in the system. So you can't multiply the energy. You can't get more energy out using a machine. You get out what you put in. Let me go back here just a second. So these three things right here, these are our main machines that we will talk about in this class: the pulley, the lever, and the incline plane. This video will talk through all of those. But three other machines that are sort of grouped within this category of simple machines are a wedge, a screw, and a wheel and axle. Wanted to make sure that if you've heard those before, you know we're not completely ignoring them, but they're a little bit more complex to do the mathematics of, and so we're going to focus on those other three. The key idea behind simple machines is that energy is conserved. So this goes really well with everything we have been talking about, how the energy that you start with should be the same as the energy that you end with. But with a machine, we will talk more about the ideas of input and output, and you're going to see that throughout this video. Work is the amount of energy that's transferred to an object or transferred away from an object. And so work input is going to be equal to work output. Again, the idea here is that however much work you do to use a machine, that's the amount of work that the machine will give back to you. In most cases, we'll be looking at a force times a distance. And so this means that the force times the distance that we are putting into the machine that we are doing will have to equal the force times the distance of whatever is being done, whatever the goal of the machine is. So you might be asking, well, what's the point? If the energy is just staying the same, what's the point of using a machine? What's the purpose of a machine? Well, let's see if we can show you that through some examples here. Imagine that you need to lift a box to a very high shelf 2 meters off the floor. If we think about what work is needed to do this, what our goal is, we are trying to lift something that weighs 1,000 newtons. Okay, so how did I get 1,000 newtons? Going back to our old weight formula as m times little g, I would take that 100 kilogram mass times 10 newtons per kilogram and see that the weight pulling down is 1,000 newtons. So if I needed to lift that up, I would have to exert 1,000 newtons upwards as a minimum. So if I'm going to do that as it moves 2 meters, I could use the work formula, force times distance, to see that 2,000 joules of work would be needed. My 1,000 newtons of applied force times the motion, the distance, 2 meters. So 2,000 joules is how much work would have to be done in order to do this job. Well, that's a lot of weight. 100 kilograms actually weighs 220 pounds in our everyday units. And maybe you can lift 220 pounds 2 meters above your head and so forth, but I don't think I could. And so that's where a machine would come in handy. You could use something like this. This is a pulley system that would actually make the job easier without changing the amount of work, which seems kind of strange. The pulley system that's shown here actually only needs 500 newtons of force to lift 1,000 newtons of weight. So because there's some different ropes here, and I'm not going to go into all the specifics, but the way these ropes are arranged, when you pull with 500 newtons of force, the machine is able to lift 1,000 newtons of weight. Now, there's a drawback because you actually have to pull more rope than you would normally. Okay, it's not just 2 meters of rope to lift it 2 meters off the floor. You actually have to pull the rope 4 meters. So the work ends up being the same. You exert 500 newtons as the rope moves 4 meters, and that's still 2,000 joules of work. So again, the input and output is still the same, but the benefit of this machine is you only needed 500 newtons. You needed less force, so it's going to make it an easier job. And that's really what a machine is usually designed to do. It's designed to decrease the amount of force that we need to do our input, and we get more force out, even though the energy stays the same. Take a look at these goats playing around on this board. You can see here when this, oh, there we go. When the one goat hits the right-hand side of this, what I'm going to call a lever, the goat pushes down because of its weight, and that forces the other side to go up. So this is an example of another simple machine called a lever. A lever is basically some sort of long object. It doesn't have to be a piece of wood, but that's kind of the common way to think about it. And it has to balance on something. That something is called a fulcrum. So other words that are sometimes used are pivot or axle, okay? But it's this point, something underneath the board that the board balances on. And the idea is that there's something you want to lift, okay? There's some sort of output that you are looking to have, and that means that you have to input something, in this case on the other side of the fulcrum. So that's the basic idea of the lever, the different parts to it. The fulcrum is the pivot point that everything sort of balances on, and then there's an input force and an output force. In a classroom, this is more along the lines of how we would set up a lever. So this will be the fulcrum. This is the thing that we're trying to lift. So that would be our output, the goal of using this machine. And then here you see me pulling down on a spring scale. That would be the input. That is what the person is actually doing, sort of the start of the machine. So again, this is typically how we will sketch out what a lever looks like. Here are some other examples of real objects in our world that are levers. Scissors is a lever. You input the force here. There's a fulcrum, a pivot point, and then on the other side is where you cut the paper. That's your output. A crowbar is often used to remove something like an old nail or something. And this as well, there's a fulcrum. It's just this point at the bottom that it sort of moves along, that it kind of pivots on. And you would pull on this side here, and then the output would be over here to pull the nails out. Now these are called first class levers. We're not going to quiz you over those exact names, but there are classifications for levers. It has to do with where the fulcrum is. This fulcrum is in between the input and the output. But here's a different thing. Here this is a wheelbarrow, and here the fulcrum is over on the side, and the input and output are actually both on the same side as the fulcrum. In this case, the input is very far away from the fulcrum, and that's the design of what's called a second class lever. In other cases, again, the fulcrum is at the end, like say your elbow could be considered a fulcrum, and your muscles are very close to the fulcrum, and that's the input, and then the output is further away. Okay, so in this case, again, the wheelbarrow, the input is really far away. In this case, the input is very close to the fulcrum. A broom is another example, kind of like your arm, where you push at a point close to the fulcrum, and the fulcrum is on the end where your other hand is, but the output is very far away from the fulcrum. And that's just called a third class lever. Again, we're not going to quiz you over which is a first, second, or third, but we want to recognize that not all levers have the fulcrum in the middle. There's a variety of designs, different types of machines that use this lever idea. But back to our more standard view of a lever. So here again is our fulcrum, the red triangle, the input force and the output force. Again, the principle behind every machine is that energy is conserved. So there has to be input work and an output work, and those two things have to equal each other. Well, that means that we're going to have to incorporate distance in here. So the input distance would just be from the input force to the fulcrum, and the output distance is from the output force to the fulcrum. And since work is force times distance, basically we just need to multiply force times distance for the input, and that will equal the force times the distance for the output. That's what we mean by the work input equals the work output. So here's another type of simple machine, an incline plane. This also has an input. The person is pushing this box, this refrigerator maybe, up the ramp. But in the end, what they're really doing is basically lifting the box. They're just doing it along the ramp instead of lifting it straight up. So the goal, the output, is just to lift it to the level of the truck, but they're doing that by using a machine called an incline plane. So what we again saw there is that the output, the goal, was to lift this weight to a certain height. But the way we were doing it was to actually exert our force along the incline. And the advantage of this, why someone would want to use an incline plane, is that because the energy is conserved, because the work input will equal the work output, the distance is long for you to actually push on the object. So it's a big distance, but that means that your force doesn't have to be quite as big. So the idea here is that if there's a certain force times distance that we need, a certain amount of work, we could sort of get that value by using a large force with a small distance, or usually we want a small force with a bigger distance. So we sort of give up the amount of distance. We kind of accept that that's going to be bigger, but in the end, we lower how much force we need, and that's the benefit, again, of a machine. Now, this was the original lever that I showed you before, and I want you to see how, although everything I said was correct, this isn't usually how a lever would be set up. In this case, the input distance is small and the output distance is big. That means that the reverse is true for the forces. The input force would have to be big, and we would get a small output force. And again, that's not usually the way a machine is designed. In most cases, we want a big force out of this machine. We want to get more force out than we have to exert. And so if we slide the stick or the plank, the wood piece down so that there's more on the left side than on the right side, more on the input than on the output side. Then what happens here is our input distance is big compared to our output distance. So big input distance, small output distance. And the reverse then is true for our forces. We get a big force even though we only have to put in a small force. And that's usually what we're looking for, again, with a machine. Now, the last thing we're going to talk about is kind of more realistic ideas with machines, because everything I've shown you so far has been very ideal. This idea that the work input exactly equals the work output. So going back to the pulley example, recall that the work that was output was 2,000 joules. We were trying to lift up this 1,000 Newton box through 2 meters. That was the goal. We used this system, this pulley system, where we only had to input 500 newtons. And because we pulled the rope 4 meters, the input work was still the same. So our output was 2,000, our input was 2,000. This is like a perfect system. This doesn't really happen in everyday life. This would be what I'm going to call 100% efficiency. What I mean by that is that if we compare the output to the input, 2,000 joules over 2,000 joules, those are the exact same, it equals 1. We would say then that the efficiency is 100%. And again, that just doesn't really happen. There's all sorts of things like we've talked about before, like things heat up, there's sound, there's friction, there's all sorts of places where energy kind of sneaks away, and we never really, in a real case, get 100% efficiency. So here's a more realistic example. We may lift this object, this 100 kilogram box, 2 meters, and so the output is 2,000 joules, but we may have actually had to exert 800 newtons of force instead of just 500. And so the amount of work that we put in might have actually been something more like 3,200 joules. And so when we calculate the efficiency, our output divided by our input doesn't end up being 1. It's only 0.63. And so we would state that as a percentage as 63%.